Hey everybody, this is a video on electrical power. And we're going to start with a question. The question is, what determines the brightness of a light bulb that's connected in a circuit? So it could be any of these circuit quantities: voltage, current, energy, resistance, or power. But let's think about what a light bulb does. A light bulb is going to take electrical energy and convert it to light energy. So if we have a brighter bulb, that means we're going to be getting more light energy, right? So we might think that our answer is energy. However, that's not going to be the case because, well, we could get the same amount of energy by just leaving our light bulb on for a long period of time. We could have a really dim light for a long period of time, and that would get us more energy. So energy is not going to tell us the brightness. What's actually going to tell us the brightness is this quantity, power. Now, that might seem strange because you might think it's at a higher voltage you're going to get a brighter bulb, more power. And that's generally going to be true, but it's not just the voltage that affects how much light comes out. It's the power. It's how much light is coming out, how much energy is coming out each second. So that's going to be power, and a higher voltage is going to affect that. That's more voltage will increase the brightness. More current will increase the brightness. More resistance, well, that could have all kinds of different effects that I'm not going to go into right this second. But what really matters is power, and that's because power is just energy over time. Or work over time, same definition as always. It has units of watts. But we want to be able to write an equation for electrical power in terms of our circuit quantities. So let's take a look at this light bulb over here. We have a light bulb. It has a potential difference of 80 volts across it, and there's 120 milliamps of current going through it. So if we think about what these quantities actually mean, current, remember, is charge over time. So that's the same as 120 millicoulombs per second. And voltage is the same as work per unit charge. So 80 volts is the same as 80 joules per coulomb. So if we want to get something in units of power, we need an energy over time. Well, we could just multiply our current and our voltage together. If we want to find the brightness, let's do 120 millicoulombs per second times 80 joules per coulomb. Coulombs cancel. We're left with joules per second. That's power. That's work per unit time. Actually, it'll be millijoules per second. And we get 9,600. The milli didn't cancel, so it's going to be millijoules per second, which is just 9.6 joules per second, or 9.6 watts. So that's really a clue as to how we can calculate electrical power, and that's going to give us our definition. Power, electrical power, is going to be current times voltage, either through the whole circuit or through an individual circuit element. The current times the voltage will give us power, and that's just because current is charge over time, and voltage is work per unit charge, so that cancels to give us work over time. So there we go. There's our definition of power, electrical power right there. However, we might not always be given the voltage. Maybe we're given the fact that we have a 20 ohm resistor and we have a certain amount of current, maybe 20 milliamps of current running through it. Then we want to be able to write our power in terms of R and I. Well, what we can do is we can actually use Ohm's law. So I'm going to bring that down here. We know that V equals IR, so if we substitute V into the power equation, we get power is equal to I times, well, V is IR, so times IR, which is just I squared R. So that gives us another expression for power. Power is I squared times resistance, we can calculate power if we don't have the voltage. Maybe we're given the voltage and the resistance and not the current. Well, then we can just say, use Ohm's law again. I equals V over R. We substitute that into the power equation. Power equals, well, I is V over R times V. We get V squared over R. So we have three different expressions for electrical power. They're all equivalent, assuming your material obeys Ohm's law. This first one is the definition, essentially. Well, the definition is, I guess, work per unit time, but IV is actually how we calculate power. The other two are just derived equations. So knowing that, we can also write a new expression for the units of power. The units are watts, and we know watts are joules per second, but since power is current times voltage, we can also write that as amps times volts. 1 amp times 1 volt is 1 watt. And we can also then do some practice problems in which we calculate power. So here's problem 1. Suppose an electric car has a bank of batteries with a net potential difference of 24 volts and a total energy storage of 4.5 times 10 to the 7 joules. If the motor draws 12.5 kilowatts, what is the current delivered to the motor? If the car drives at a steady 16.0 meters per second, how far will the car travel before the battery runs out of energy? So I'm going to just sketch out a diagram of the circuit. We have some bank of cells or batteries, and then we have some load out here. I'm going to draw it just as a load. It's actually going to be the motor, but it has some resistance. We might model it as a resistor, but it's not really a resistor because the resistance will change at different currents, so it doesn't act like an ohmic resistor. But anyway, this is 24 volts, and we have a total energy storage of E equals 4.5 times 10 to the 7 joules. The motor draws 12.5 kilowatts. We want to know what the current is delivered to the motor. Well, so for part A, we're given the power, we're given the voltage, and we want to find the current. We can just use P equals IV. Since we're finding the current, we solve for I. We get I equals power over voltage. Our power is 12.5 times 10 to the 3 watts, 12.5 kilowatts. And our voltage is 24 volts. Watts divided by volts. Let's just plug into a calculator. 12.5 times 10 to the 3 divided by 24. Getting 521 amps of current. Ooh, that is a whole lot of current. That is more than enough to, way more than enough to kill you. This is a whole lot of current. So we have 521 amps of current. B, if the car drives at a steady 16 meters per second, how far will the car travel before the battery runs out of energy? So in part B, we're given that the speed is 16.0 meters per second. We want to find the distance traveled before it runs out of energy. Well, to get the distance, we can use speed is distance over time if we know the time. Now, we don't know the time, so let's see if we can find the time. We can use this other fact about power from our definition of power. Power is just going to be energy over time. We know the power, we know the total energy, so we can find the time. So that means our time is just going to be energy over power. Our energy is 4.5 times 10 to the 7 joules. And our power is 12.5 times 10 to the 3 watts. This will give us our time in seconds. Getting 3.6 times 10 to the 3 seconds. Wow, that's actually a really coincidentally round number. Because if we wanted to convert that to hours, there are 3,600 seconds in an hour. So that's just equal to, well, 3,600 seconds times 1 hour over 3,600 seconds. So our time then is just 1.0 hours. Now that we need to use hours to do this, let's actually just find our distance. So from speed is distance over time. We can solve that for distance. We get distance is speed times time, which is 16.0 meters per second times 3,600 seconds equals let me write it down here. Distance is 5.76 times 10 to the 4 meters, or 57.6 kilometers. There's our answer. Just application of our equations for power, electrical power, and speed is distance over time. Let's look at question 2. A 1280 resistor is rated at 4.50 watts. What is the maximum current through the resistor? And at this value of maximum current, how much charge passes through the resistor in 1.5 hours? So we have our resistance is 1280 ohms. Our power rating, our power rating is 4.50 watts. And we want to find our maximum current, I. Well, we have an equation for power in terms of I and R. We know power is equal to I squared times R. So if we solve that for I, we get I squared is power over resistance. And therefore, I is just equal to square root of power over resistance. Which means that our maximum current is just going to be the square root of 4.50 watts over 1280 ohms. It's going to be 5.93 times 10 to the minus 2 amperes. We can also write that in milliamperes if we want, because usually milliamperes is more appropriate. That's going to be 59.3 milliamps. Okay, there's our answer for part 1, or part A, I guess. Part B. At this value of maximum current, how much charge passes through the resistor in 1.5 hours? Well, so we know that the time is 1.50 hours, which we might want to write in seconds. That's just going to be 1.5 times 3,600, because there are 3,600 seconds in an hour. It's going to be 5,400 seconds. And we can use the fact that current is just charge over time. So the total charge that passes is just current times time. Or we could say 5.93 times 10 to the minus 2 amps times 5,400 seconds. I'm getting 320 coulombs of charge in that amount of time. So there's some power problems. Remember, P equals IV, and you can always use Ohm's law to derive the other two equations for power, although they are given on your equation sheet. That's all. Bye.